Next, we have our first keynote for today. The keynote is by Mr. Niladri Roy. He's in charge of robotics and AI for Intel PSG Industrial Unit. He has flown in from San Jose for this conference, and his talk is going to be about integration, acceleration, and roadmap to single chip implementation. So I welcome Mr. Niladri Roy to give his talk.
Thank you, Prati. So good morning, and thank you for being here. It's heartening to see large audience, and those of you thought you'd escape my presentation by arriving late, the organizers shuffled the agenda. So you missed that. Thank you. So with a quick introduction, I was made aware this morning that there's a college called PSG locally, and just wanted to make sure, to avoid any confusion, that the PSG that you see over here does not have a relation. PSG stands for Intel Programmable Solutions Group. So with that out of the way, I just wanted to share with you my initial trepidations when I was requested to provide a keynote address. The keynotes are hard. Talking about technology, talking about marketing stuff, what our companies do, those are easy things. The reason why keynotes are hard is you can't play the entire opera. It's one note. It's one note that has to be key. And it has to be key, it has to be relevant to what you guys do. So with that, I wanted to build a message on something that I alluded to briefly yesterday during the panel discussion. And that was that if you wanted to do something that would help robotics, you would want to do integration and acceleration. And this is about that. So I'm hoping not to bore you with marketing. I'm hoping not to talk a lot about what we're doing in this space. I want to keep it very concentrated into integration and acceleration, and hopefully not at a very great price. And at the end of the presentation, you can ask me questions. If it has to do with technology trends or implementations of what we do, I'd be happy to answer. If you've got detailed technical questions of how one bus interacts with another, you'll have to talk to people who really know something. So then I'm going to take your questions back and get them answered. So without further ado, oh, how did that happen? Okay, got it. So without further ado, I want to refer briefly to something that came up yesterday, and that was heterogeneous compute. And people really wanted to talk about integrating features like CPU features, GPU features, DSP features for controlling a robot. Now, if we look at these technologies, the CPU essentially is a sequential machine. I mean, those of you who are as old as I am probably know that the standard CPU algorithm is to begin, fetch the next instruction, execute this instruction, go to begin. And it keeps doing that again and again and again. But if the instruction is long, or if the instruction is multi-worded, there's a finite execution time, A, and B, instructions have to precede one another. They're in a queue. So essentially what you're doing is sequential. You can have multiple lines, but that's besides the point. What you can do in a GPU is you can, given the type of workload, break it out into a lot of instructions that are being processed in parallel. Makes things really fast and exciting. And finally, you also have a technology that is the one key thing that I introduced today. And because my experience is that I have seen people work with CPUs, I've seen people work with GPUs when they're talking about robotics or trying to implement something robotic. But I do not see FPGAs being leveraged, and that's a pity because you can do a lot more and you can do it probably a lot faster in many situations if you use this particular technology. Because FPGAs are massively parallel, but notice it says programmable circuitry. So I'm going to spend a little bit of time on my next slide explaining what an FPGA is, but do understand that an FPGA starts out as a blank slate, and you can program actual hardware onto it. So you're not programming software, you're not providing instructions to hardware that's already in a chip. You're taking a blank chip and making a circuit on it. So if I were to describe an FPGA to people who are not aware what an FPGA is, an FPGA starts out life as a sea of gates. And within that sea of gates, what you can do is you can connect them, and you can connect them with interconnects. Excuse me. Can you have this on, please? So when you connect these blocks in an FPGA, you create what's known as logic block. And an FPGA can have many logic blocks with interconnects in between. And there will be usually columns and columns of logic blocks within an FPGA. So these are all blocks that you can create, that you can connect to create circuits. Many of you are aware that essentially you need one NAND gate, and you can create all kinds of circuits from multiple NAND gates by connecting this. That's what it does. But that's not where FPGAs stop. FPGAs can also have embedded memory. They can have DSP blocks, and they can have external memory controllers as well. So an FPGA can have many logic blocks, it can have DSP blocks, it can have embedded memories, it can have external memory controllers. It can even have hard IP blocks, meaning that here you're not really creating the circuit yourself, but you realize that the FPGA would be better if you had something like, say, a PCI Express block on it. Or if you're going to use it for AI, maybe a tensor block on it. So they can have hard and soft blocks. They can also have transceivers. So if you want to use gigabit for communicating to the real world, you could. You don't need to use gigabit, but yeah, you could use gigabit transceivers within an FPGA as well. Beyond that, you could have PLLs, you could have a hard processor block. This is when it gets interesting to you guys. Because now, for the first time, you're seeing a guy who's going on and on about FPGAs say that there is actually a CPU in it. Now, all FPGAs do not have CPUs. When an FPGA has a CPU, we call it as SoC FPGA, meaning a system-on-chip FPGA. But now, what you have is something that's completely programmable, which can even have an analog block in ADCs usually, and which can even have flash memory. And basically, you can use an FPGA and connect it in any which way you want to realize that circuit that you wish to realize in double quick time than it would take you to build a custom ASIC for this application. Now, you're probably aware that ASIC geometries have gone down, they've become smaller and smaller. It's become very expensive to build an ASIC. Whereas an FPGA is sort of a blank slate that's provided to you, and you can build your quote-unquote ASIC within it by programming and reprogramming it. So yeah, what is the penalty you pay? It's not going to be as fast as an ASIC. The ASIC is going to be the fastest. Sometimes you can even tune the power of your ASIC, but FPGA is a technology that I believe roboticists can use to run operating systems like ROS2 on the HPS and run other hardware that is necessary for your robot to work within the rest of what we call the fabric. So typically FPGA engineers tend to refer to the hard processor system as the processor, and the rest of the FPGA consisting of logic blocks, memory controllers, and everything else, DSPs, what have you, as the fabric. So today, if you look at the architecture of your robotic systems, yeah, you have some kind of a CPU which is running some kind of an operating system. Doesn't necessarily have to be ROS. I have seen many robotics implementations who run their own, but they also have ingest, which could be visual ingest from, say, cameras, multiple cameras, LiDAR, and they have, of course, motors to run and operate in the real world. If we take just one kind of example, an industrial robot, a 6 or 7 axis robot, that's going to have that many motors which you need to control. Now, you know that your ROS2 can compute the motor states, and what you'll need to do is you'll need to send out these motor states to the robot. The one thing that the FPGA will not do, I need to caution you, you do not connect it directly to the robot because there is power electronics in between. So you connect it to a power board, which then can connect to the robot. But if we look at the robotics performance boost areas that we can get with FPGAs, one is ROS2 integration. So you can run ROS2 on the hard processor system. The second is acceleration of the entire networking stack. You can even do AI acceleration. One, because you have a parallel device, a massively parallel device. And also you have things like tensor blocks, which we build and put in there to make AI easier. You can achieve better timing synchronization, and we already talked a little bit about motor control. So at this point in time, I do want to let you know that what I say and what you see on the slides may differ slightly. Doesn't mean they're divergent, but it means that what I say and what's on the slide has to be taken together. I am certainly not going to read all of that content out. So this is the advantage that we can get in performance boosts, and we can look at some numbers later. And if we were to look at what we get, and this can get extremely contentious in a forum like this, I do not want to turn it into a benchmarking tirade, but trust me, and you'll have to trust me on this, you could go to our website and look up all of this, but you would find examples of tightly coupled ROS2 with FPGA fabric, and then you would find the 10 to 15 times cycle time improvement that you can have on protocol like, say, Ethernet, EtherCAT, Profinet, and so on. AI acceleration, you will ask me what is it compared with. I deliberately I removed what it is compared with. I certainly am aware that I'm operating in an environment where there are multiple companies over here, but that's just an example of the kind of improvement you can get over other technologies. And you can also offload things from a CPU into an FPGA, or if you're using a SoC FPGA, even offload the hard processor to get synchronization in scenarios where you have, say, multiple input streams which are visual, which could be cameras, which could be even LiDAR. And finally, in motor control, you don't have to buy a motor control chip from Allegro or TI or NXP. Not that they make bad chips, they make great chips. But motor control is such a thing that most chips kind of do 2-axis kind of okay. Most do single-axis. Some of them do 2-axis very well. And you will find on the websites of motor control manufacturers 3-axis simultaneously, but in my experience, those kind of die at 2.5. The good thing about FPGA is FPGA, I told you, is a blank slate. So if you have a small FPGA and you have just enough space in it to fit in one motor control circuit, fine. If you have a bigger FPGA and you fit in a second motor control circuit, there is nothing sequential about the operation. Everything is parallel. Just as we looked at, the CPU was do begin, get the fetch the next instruction, execute this instruction, go to begin. An FPGA doesn't follow that sequence. The best and crude example I can give you is if there are 10 lines of code or 100 lines of code in an FPGA and you turned it on, all the 100 lines execute at once. So if you have, instead of one motor control axis, 8 axes in there, they will have zero, and I emphasize absolute zero impact on the time the FPGA would take to operate all those motors. Now that makes for a very interesting situation, because we talked a little briefly about it yesterday, that it is okay that we use $20,000 robots and $40,000 robots to do stuff today. We cannot keep doing this forever. What we need is not even the $8,000 robot we can get from China. What we need is a $1,500 robot. And for a $1,500 robot to operate, my electronics has to scale down in price, and my control has to be guaranteed to operate between robots where the manufacturer tolerances are going to vary widely. So which means that the bearing frictions of these axes are going to be different. The moment of inertia of the arms are going to be different. Gear hysteresis is going to be different. And I need methods like model predictive control instead of PID to operate robots. Now that's not the easiest thing to do, even with CPUs. Like Intel sells a lot of CPUs into the robotics market. But how many customers can think of building a $1,500 robot with a $2,000 CPU? Can't do it, physically impossible. So this is why I wanted to introduce you to the FPGA. And I just wanted this slide to tell you about what the application trends are and what those trends require support for. And this little bit of marketing, if you'll allow me, that we will talk about the Intel Agilex 5 FPGA, which comes with 2 processor complexes. There's a dual A76 and a dual A55. And you also have an AI tensor block in it. But importantly, you also have a lot of supporting IP, for example, like MIPI for cameras, or say TSN or Profinet or Ethernet for connecting to the real world. And you also have motor control intellectual property that you can execute in a device like this. From a price standpoint, yeah, it tends to eat into some of our own stuff in CPU. But you know what? It is better to enable the $1,500 robot than hold back an entire industry because you will not talk about a cheaper solution. So the whole point of the keynote is you looked at CPUs, you looked at GPUs, look at FPGAs as a potential item that you can use. And yesterday I talked a little bit about we being semiconductor companies. At the end of the day, we sell silicon. Sometimes we do make solutions. They are not as great solutions as somebody who has proven competencies in a particular area will make. For example, SEW Euro drives is always going to make better motor control than we do. So the point when we create solutions is not to show the world, oh, Intel can do that, or not to compete with our customers, but to do 2 things. One is we create a proof point, and sometimes when we get lucky, either we ourselves or work with our partners, we are able to create a halfway point of code that you can pick up and use. So with that in mind, we had a robotics roadmap, and what you see is something that started as a drive on chip and which ends as a robot on chip. Some people who like kind of words call it talk to rock. I don't particularly like talk to rock, but it is a drive on chip to a robot on chip. And what we did was we started by creating multiple axes of drives on chip. And then just to spice things up a little bit, we worked to add a Cat3 PLD safety concept and called it a safe drive on chip. And we got it certified by TUV Rhineland. So today, many of our customers just pick up the drive-on-chip design and the safe drive-on-chip design and directly use it in their systems. Of course, that is not their entire system. They build a lot of other things. And then we realized that we've been also working with PLC manufacturers for a long time. So why not integrate the PLC? Because we believe there's space on the chip to do that. So we integrated the safe drive on chip and the PLC. And then we added just the equivalent of a teaching pendant, and we called it a consolidated robot controller. Where we want to go from here, and I think you will see manifestation of this in 2024, is the complete robot on chip. So that, supported by the Intel tools, is the goal for 2024. The consolidated robot controller, it contains the robotic subsystem. It actually has a robotic application and ROS running on the HPS, or hard processor system. And then alongside it sits the drive on chip subsystem, and you can have n number of stacks after it. As I said, I'm not going to read out the entire content, and I'm sure the content is going to be available to you later. But this is an example where you can take a reference design like this, which will be available in the first half of 2024. And actually, in a way, it's available now, but it's available on an older technology, not on the Agilex 5 that I talked to a little while earlier. And I think you guys would be better served by considering the Agilex 5 than one of the older technologies. But on the Agilex 5, you should have that design available as a reference design that you should be able to download from our website by the first half of 2024. And then, yes, there is a little bit of an investment in learning the FPGA tools. Yes, it's going to be counterintuitive. You're used to programming a CPU. Here, you have nothing. It's like drawing a circuit on a page. You're programming that circuit onto an FPGA. So there will be a learning curve. There will be a transition that you would need to make. But if you did that, you would be able to modify this design, which could be written in Verilog or VHDL, and create your own robot controller. What we want to do next, and here we're working with one of the organizers of this event, Acceleration Robotics. What we'd like to do next is build extensions and use FPGA acceleration into the ROS2 ecosystem. And the way this is achieved is Acceleration Robotics actually first looked at what are the primitives that we can accelerate in robots. Now that work is by no means complete yet. But once you complete that, the second thing that you look at is, okay, so which are we going to prioritize? And is it MOVE-IT or is there some other algorithm? What are we going to accelerate in the FPGA? So not only do we now have a device which is able to run something like ROS2 in the hard processor system and the motor control, the networking, the safety, the security, the video ingest on the rest of the fabric, we have a new twist that the ROS2 functions are actually going to be accelerated within the FPGA. Now, I can guarantee the robot on chip being delivered in 2024. I don't know how much of an acceleration library we can deliver in 2024 because it's a lot of work. But if this group adopts FPGA or even experiments with FPGA as a way to work robotics on a single chip, I'm fairly confident that some of those libraries are going to start coming out of this group itself. An example of stuff that Acceleration Robotics is doing with us is, this is part of their robot core acceleration for ROS2. And what they have with us is a FPGA-based ROS2 implementation for high-speed networking. That's one example. And this implements the ROS2 framework in hardware, and it delivers speeds of less than 2.5 microseconds for send and receive. Now, that's typically 62 times and in some cases up to 1,000 times. And there's a disclaimer at the bottom that we haven't verified all the claims, but we believe acceleration robotics. So we believe that accelerating ROS2 within an FPGA, you can have faster processing of data, you could have reduced latency and improved synchronization into your robotics projects. So I wanted to recap a little bit as to why you would want to use an FPGA in the first place again. Number one is you can alter the FPGA circuitry anytime you want. Now, this may be counterintuitive. The same FPGA could be in a wireless router, and it could be in a camera, because it started life as a blank slate. It came to you, you reprogrammed it. The funny thing is, you could reprogram it again and again. An FPGA, when a device is off, when something you've built with an FPGA is off, the FPGA has no memory of that circuitry, usually. What happens when you turn that router or that camera on is there's a little EEPROM that immediately transfers what we call a bit stream, and that is an instruction for the FPGA to configure itself in the way that you intended. And once the FPGA is live, and that is within milliseconds, it becomes a completely different device that you intended. So you can alter, you can make improvements to circuitry that you've built at the FPGA at any time. And this is a massively parallel device. You can accelerate anything that you can parallelize, and you can, for example, keep adding multiple motor axes without any performance penalty at all. You have the flexibility of changing the circuitry that we just talked about. But apart from motor control and running ROS2 on the hard processor system or HPS, you can add functionality like connectivity, safety, security, and other interfaces, which might be specialty interfaces, like, say, in redundant environments, you need that robot to work. You could add HSR-PRP, which stands for High Availability, Seamless Redundancy, and Peripheral Redundancy Protocol. So there is no limit to what you can reprogram the FPGA with. So it makes a great choice for accelerating functions and for adding functionality as well. So that pretty much brings me to the end of this talk, with the exception of one slide. And this is just a summary of where Intel's operating in smart manufacturing, which is industrial robots, in warehouse robots, in agriculture, robotic surgery, and a couple of other places as well. We work with a lot of partners, and our ecosystem consists of intellectual property from the partners. It also consists of SOMs, or systems and modules, that our partners build. It consists of hardware and software designs, part that is built within Intel and part that is built by our partners. What our partners build is not necessarily free. Some of it is free, but most of them, that is their bread and butter. So expect to pay for partner designs. The designs that we manufacture and make available on our website, those are free for use. And there is an entire suite of software, which, as I said, is a learning curve you'll go through when you look at FPGAs as an viable, much better alternative to CPUs. And there are a number of silicon platforms, starting from our very high-end Stratix devices to Agilex and the older Cyclone and Max devices. Max is one of the devices that has the ADC and the flash memory built in. And also eASIC. eASIC is a relatively, and I use the word relatively because they've been around for years, but they're a relatively new concept compared to FPGAs. So if you built an FPGA and you tweaked the circuitry over a period of time, and maybe after a few years decided, I'm pretty much done, this is going to be my standard circuit, you can actually, instead of using an FPGA, transfer the same to an ASIC through Intel, and we call that process creating an eASIC. And the reason why you'd want to do that is it did not have all the costs of creating an ASIC. It is already proven because you've been on the field for a number of years, but it's much cheaper to manufacture per unit as an eASIC than in an FPGA because it doesn't have to be reprogrammable anymore. So those are some of the silicon platforms, and it would not be right to say if we didn't talk of the AI roadmap and the long life cycle. Many processors tend to go, and including our own, tend to go EOL or end of life in 5 to 7 years. FPGAs that we manufacture have a lifetime of 15 plus years. In fact, some of the legacy FPGAs that I just talked about, because of customer demand, we announced several months ago that we will continue to manufacture those FPGAs till 2035. So this is a technology that is malleable, that can be extremely fast, can be much cheaper than even our own CPUs and GPUs, and except for the learning curve, is ready for you to experiment with. Thank you, and any questions?
So we can have a couple of questions.
Good morning, sir. Right. So thank you for the introduction to FPGA. And I am actually from mechanical background, so I don't know much about embedded systems. My question is in two parts, sir. First one, usually, although the computing mechanisms are fast, we need mechanical systems that usually respond slower. Even on Arduino with a 16 MHz processor, we often tend to give delay to the instructions because the motors are not fast enough to actuate. And the second part is, most of the PCBs or single board computers or embedded systems are very sensitive to the power fluctuations, even for the sensor data or from the battery supply. And how stable is FPGA technology for those power fluctuations?
So I would say that FPGA technology has the same issues with power fluctuations as any other semiconductors. However, we manufacture FPGAs in several grades. One of them is commercial, but the other is the I grade or the industrial grade. And there are some automotive FPGAs as well. So there are different environmental tolerances that you can buy FPGAs with. And we have a number of customers who might be using an automotive grade FPGA where the application is not automotive at all, but because they want the additional environmental protection that FPGAs offer. One thing we cannot do is bend the laws of physics. So the best thing that we can do is have these different grades. Obviously, it costs more money if you want to buy a more environmentally protected grade, but they like every other electronics, are vulnerable to environmental conditions.
Any other questions? Yeah.
Hello.
Yes.
It's a great idea to put an FPGA and run it, correct? But my worry is the tools required to make FPGA, commercial tools, are very expensive. Correct? If I want to go to Synopsys, buy a VCS for simulation and plus routing planning and all that stuff, it costs more, correct? If you look at most of the software engineers, they use a lot of open source code to develop any robotic application. We come from an EV truck manufacturer. We use most of the open source solution to make our vehicle move. And FPGA is a very great solution because I see in our current system itself, we don't have enough juice to run it. I run an 8-core ARM core and an NVIDIA AGX with a 512 core GPU. Still, we don't have enough juice to run it. FPGA is a great product, but the tool support is very expensive. And the mindset to develop an FPGA is totally different from writing in a software. The way I give an example is like writing a software is like an MP3 song. The writing in a code in RTL is like watching a movie, watching a picture, correct? It's all parallel. So I don't know, unless we get cheaper tools for this, I think still it will be a little bit difficult for, especially for the startup companies. What's your
First of
take?
all, thank you for articulating my greatest challenge. Yes, the FPGA tools they represent the main barrier to entry, but they're not necessarily expensive unless you're buying tools from third-party vendors whose business is tools. You mentioned Synopsys, but there are a lot of FPGA tools that you can get for free from Intel. Is everything free? No, some FPGA tools cost money, but you know what? If we are trying to program $1,500 robots, I don't really see a scenario where you would need those priced tools. You should be able to just put in your name, your company, etc., and download Quartus Prime, which is the Intel's FPGA tool for FPGAs. You could download it for free. But getting people to use them, that's frustrating, because if you're a sequential CPU programmer, you tear out your hair and say, how the heck do I program this thing? So yes, there is this learning curve, but it's not even as hard as I make it out to be. The reason why I say it's frustrating is I don't want to leave you under the false impression that you choose an FPGA over a CPU or a GPU and everything is great. There is this transition, there's this cost that you're going to pay. But for the same performance, and I hate to say same functionality because there's no fixed functionality in FPGA, it does whatever you want it to do. But for the same performance and the advantage of flexible functionality, at the same price point, there is no solution even with Intel CPUs. What you can do with an FPGA at a certain price point is going to take a much more costly CPU to do. And I'm not going anywhere near GPUs because depending on the scenario, it might be, you might find the tools easier. But once you overcome the tool barrier, and if you really want to differentiate what you're making, because everybody and his brother is able to program in ROS2, and the lowest, the path of least resistance is to go and just program in ROS2 and run it on a CPU. Does it give you the cost advantages? Does it give you the ability to tailor your particular robotics product to your specific application? Does it allow you to run 8 axes of motor without slowing things down? Because now instead of one motor, you've got multiple. And if you wanted to do things like, say, model predictive control, we really didn't go there, but that is the entire answer to the PID loop not working on cheaper robots. But if you wanted to do very high compute intensive functions without the known compute answer, which is CPU, how would you do it? So there are benefits that you can get from the FPGA. And if that was one key and note that I had to strike, I think I struck that. I'm not going to pretend that it is easy, but what the heck? There are 10,000 plus FPGA customers that I can, I see in every quarterly report that comes out. And if people are getting an advantage out of it, and if these customers are people like Siemens and ABB, they must be seeing something in an FPGA and the reason why they want to use it. So it is both small companies as well as large companies who use FPGA. Most times, smaller companies use FPGA because they want to gain strategic advantage. Brains of Crossing the Chasm by Jeffrey Moore. Yeah, the smaller companies tend to use FPGAs for strategic advantage. The larger companies, because they can employ an army of engineers, they can throw engineering resources, the labor resources of engineering at the problem. So yes, it's not for everybody, but it depends on, it's a trade-off, What do you want to achieve? Do you want to get the benefits? If the benefits of the FPGA is important to you, then you probably want to use an FPGA. But what I'd hate to see is you not considering an FPGA at all because nobody explained to you what it can do. So that's what I wanted to achieve today. That second slide where you saw the FPGA building, I think that's That's important for a lot of people because you otherwise don't know what these chips are capable of doing.
Okay, thank you. I think we don't have time for more questions. You can ask your questions offline to Niladri, sir.